And now I would like to invite Romeo Valentin, who is going to present us a talk on algorithms for validation of dynamical systems. He's a PhD student at Stanford Intelligent Systems Lab.
All set up now. All right. Yeah, welcome everybody to this talk, my talk today on algorithms for validation of dynamical systems. Thank you for the introduction. It's true, I'm Romeo Valentin. Yeah, and I'm part of the Stanford Intelligent Systems Lab. Here's my beautiful group. And maybe you know, some of you might know our professor, Professor Michael Kokendorfer. You can see him there over to the right, kind of. And one thing that Michael has done over the years is write a bunch of books which are actually using Julia as a core part of the books. So Michael wrote a book on algorithms for optimization, a book on algorithms for decision making, and now our lab is releasing a new book. It's currently kind of in the publishing process, algorithms for validation. And one of the really cool things about these books is that actually they have these algorithms and they do the math and they do the motivation for them, but actually instead of giving pseudocode implementations of kind of the different algorithms in these books, it's always actually an implementation in Julia. With the idea kind of that Julia actually is a really good representation of pseudocode, and usually you can kind of go into this book or do these books, kind of take the algorithms, copy them into your code, and run them for the most part. Okay. And so before we continue, I also want to thank actually the authors of the book. So I didn't write this book, but my colleagues at my lab did. Michael, of course, but also Sydney, Anthony, and Robert. I don't know if you can read it there. In the right of the book. So Robert was here actually also yesterday giving a talk on using Julia for teaching. Maybe some of you saw him. He's unfortunately already gone. But if you have a chance to talk to Robert about these things, I can wholeheartedly recommend it. All right, so algorithms for validation of dynamical systems. So what is a dynamical system for the sake of our talk today? Here are two examples of kind of very simple dynamical systems, right? So when I say dynamical system, I mean we have some system that we kind of roll out in time, we kind of step forwards in time. So we have some system environment that we have a pretty good knowledge over the system dynamics, or at least some kind of simulator that lets us kind of do this rollout. And then we have an agent or a controller, you could say, maybe some PID controller, maybe some data-driven controller, and really any black box controller that kind of does something here. And then maybe we have an observation model, which might be noisier or something like this. Yeah, and so here are two examples of dynamical systems. For example, we have the pendulum, a very classic kind of one-dimensional control problem. On the right, there's a kind of a more interesting problem, a collision avoidance system. So that's kind of very near and dear to our lab, right? So here the goal is to kind of fly the airplane, and you encounter another airplane on a collision course, and the idea here is to kind of avoid a collision with the other airplane. So these are two simple examples, but actually the topics in this talk and this book really extend to a very wide range of dynamical systems. So you could, for example, think about having maybe a stock market trading bot there. So you have the dynamical system, the stock market rollout, so to say, every time so you make investment decisions. And you usually want to keep some kind of safety property true. So for example, your portfolio shouldn't go to zero. Maybe you have a control problem in a power plant on a chemical reaction network, right? And you want to kind of control the temperature or something like this. Yeah, and so in the end, for us, it's kind of all the same. And what is interesting to us now is how can we validate the systems in kind of these safety critical applications, let's say like a power plant or like a collision avoidance system. In particular, in the setting where we have kind of black box controllers and maybe black box environments. So when you have kind of very white box controllers, maybe you understand a lot about let's say the PID controller that you're using in the setting, or you have kind of a very good state space analysis, then you can maybe make some really mathematical and well understood argument that will kind of help you convince yourself that you have a safe system. But it turns out that kind of in the current day and age, more and more people are using these kind of black box models, let's say data-driven models, to do these kind of control designs, let's say. And then, for example, one example where this can come up is, let's say you build actually this collision avoidance system, and in our lab we have something like this, and then you come up with like a great kind of planning algorithm, and you try to make it fast using some neural network, something like this. And then you go to the regulator and you say, hey, I want to put this into the airplanes. Maybe the United plane or the Delta plane that you all are gonna fly home later this week with today. And then the regulator says, okay, hold up, we cannot just put anything willy-nilly into the airplanes that civilians use. So the regulator, you can try to do a lot of analysis, but in the end of the regulation, usually what the regulator asks of you is to give them a probability of failure, let's say catastrophic failure, that your system during the rollout will have some kind of, let's say airplane collision. So I want to ask you all to give me kind of an estimate. What do you think is the FAA's statement, one failure in so and so many hours is kind of the accepted tolerance in the aviation business? So maybe it's one failure in 1,000 hours, in 1,000,000 hours, in a billion hours. What do you guys think? What's that? Million, yeah. Yeah, so I heard million. That's kind of true. So usually something in 10 to the 7 to 10 to the 9 hours. So, similar order of magnitude, let's say. So we can look here, for example, at just as one example of the kind of Del A certification spec. And so here we can see the probability that they ask for kind of a catastrophic failure to occur is one failure in 1 billion hours. So that's very little. And now a little side fun fact. Now you can actually go ahead and you can kind of count how many hours of commercial flight there is every day, let's say in the US or maybe in the world, and you come up with something like 100,000, 200,000 hours of flight every day. By itself, already interesting number, I think. And then you can see, okay, so how many days of operation do we need to kind of get to 1 billion hours of flight? And it turns out that it's, approximately 10 years of commercial aviation to get kind of to this number. So if everything works, we have, everything is FAA certified, and then we have approximately one catastrophic airplane failure in 10 years. Now we can kind of think, is that true? I would say it's maybe off by one order of magnitude. But I think it's actually very, very impressive that the FAA kind of, can even achieve numbers in these kind of realms. Okay, problem is now we are the engineers, right? Maybe we're all engineers here, and now it's our burden of proof actually to show that our system has a failure rate of 1 in a billion. Well, that's pretty tough. So one thing you can try to do, of course, is you can just kind of roll it out for 10 hours, 100 hours, 1,000 hours, 10,000 hours, your company goes bankrupt, get some more investment, 1,000,000 hours. And even if you have no failure until then, the regulator will still say, okay, 1,000,000 hours, there's still no failure in 1,000,000 hours. We're looking for, something even greater here. And so this is kind of the core challenge that we're trying to address with these algorithms for validation. So really, we're gonna talk about kind of two things today, and I hope it gives you some nice ideas maybe for your own work. So one question will be, okay, how can we actually find failures, even if they're kind of very rare, but how can we still try to make our system fail somehow, and then kind of understand how these failures occur, and then also how can we estimate the probability of failure over kind of the entire system without having to roll out, let's say, 1 billion hours, and maybe being somehow more sample efficient. Okay, so the little example we're going to use today is just a little controller lying around. So this is kind of a very classic control problem. So we have here, the car pole controlled by some neural network controller that we trained in Python, let's say. And so I want to point out a few kind of interesting things here, what I mentioned before already. So sure, we're in Julia, we're at the JuliaCon here, but actually this talk, let's say, is more about Julia as a way of implementing very nice algorithms. It's not so much about, let's say, the efficiency and so on, because actually the simulator, it's not running Julia, it's some kind of black box simulator. You don't need to know actually how it works. This is some Python call interface through the OpenAI Gym. And then also the controller, similar thing, you have a black box controller, you don't really understand maybe how this neural network works, you don't understand the failure regions of it inside somehow. And so you need to deal with it in this kind of black box setting. Great, so now we're kind of starting to roll out some trajectories here. Maybe we can resample another trajectory. Okay, looks pretty good. Let me get another one. Okay, looks pretty good to me. And so yeah, the most kind of obvious way to try to find failures, as I described, is just through kind of very naive direct falsification. So I'm showing this example more as kind of a didactic example to understand how the code works. or the algorithms work, okay, we have just some statement here, is failure of some specification. So we say, for example, the pendulum is not supposed to fall over, and then our whole trajectory. So we always, make a statement about the entire trajectory. Then we have our struct, which we can dispatch on to kind of do the falsification. And then we have a very simple algorithm, okay, m times, some let's say 100 times. We do a rollout of the system, and everything is nominal noise, nominal, control, everything. And then we just see if we found a failure. So this is kind of, the approach of we're going to try to roll this guy out a billion hours or 10 billion hours or something. So let's see what happens. We can run it here. Oh, empty list. So we found 0 failures. Maybe that's expected. But so this is a little bit like going here, and resampling this guy a bunch of times. And now what we actually want, we can basically resample this many times. But what we want is we want to sample the failure. So let's click the sample failure button. Ignore the warning at the bottom. Aha. Let's check it one more time. Yes. So this is what we're interested in. How can we get a case like this where we actually have found a failure, even in a setting where the failures are quite unlikely? So this is the first thing we're going to talk about, and then we're going to talk about overall failure probability estimation. Okay, so to do the kind of failure finding, one of the ways that the book proposes, let me hide this for now, is through optimization. And for optimization, we kind of need an objective function. And it turns out that we can make a very nice objective function by kind of formalizing the idea of the specification and then going straight off that. So the specification here is something like, okay, we want to always, at every step of the trajectory, we want to have an angle between minus 12 and 12 degrees, let's say. And in Julia, we can use this really nice package that Robert wrote, signal temporal logic, and then we can write it, very nicely, very Julian kind of in this kind of spec. And I just want to note that in this kind of framework of signal temporal logic, there's actually many other nice things we can do. So there's always quantifier eventually until we can specify certain time ranges. You can kind of aggregate conditions with like an AND operator or operator, or have kind of a bunch of a bunch of temporal logic operators. And then we can use this. We can use this in our objective function for some kind of optimization. So now we want to do falsification through optimization, and the idea here is, how about we take the specification we just said, we're gonna kind of smooth it out a little bit, so we have this row operator. Okay, it's just kind of saying how much are we, instead of just saying yes we are or we are not in the spec, how much are we in the spec, and then we're going to make it a little bit smooth by saying the always quantifier, we're going to actually replace it by a softmax. And there's kind of this automatic translation that you can do, and this package will do for you to kind of turn the specification, which usually just gives a true or a false value, to turn it into a continuous value. And then you can just plug it here into your optimization objective. At the same time, maybe you say, okay, I also want to find failures that are at least somewhat likely. Maybe they're not very likely, but let's also put the likelihood of the failure into the objective function. And then you just say, okay, we want to optimize over our initial state, over the observation noise that we see at every time step, right? Then we have a variable here, we do a rollout, and then we kind of measure for the rollout how much is our spec violated and kind of how likely is it. Great, and so this, we can put this super nicely into Julia. So here we're using the kind of SciML optimization.jl with the optim.jl optimizers, okay, anyways. And then we make a nice optimization function. We can even ask for automatic differentiation using finite diff if you don't have kind of the gradients available. And then you optimize over this U. In this U, we just unpack it to be our initial state and our noise at every step. Then you just roll this guy out, and then you measure, the term that we just discussed, and there's your optimization. And so I think one thing that's really amazing here is kind of if you factor this idea correctly, and I think this book really, one of the main values of the book is this kind of really clean factorization of this problem. Great, so then you have the objective function, you define some struct to kind of dispatch on again, let's not get too hung up on it. And then You have the falsification algorithm again, so similar to the one we had before. Okay, we kind of shuffle around the parameters a little bit. We make our optimization problem using the optimization function from above. And then we can just sample trajectories by always getting a new initial condition, the U0, and then just solving it with our optimizer. This will give us the noise trajectory. Then we can use the noise trajectory to get the actual kind of trajectory. And then in the end, we just filter again for failures. So if you ask me, this is a really beautiful kind of, concise way to write down what we're trying to do here. So let's try it out. Okay, we're gonna, get our structure, and then we can just run this guy. Takes about 10 seconds. So we're doing 3 falsifications now. Oh. One more time. Come on. Suspense is rising. We're getting there. Okay, there they are. So we find actually, 3 out of 3 successes in getting optimized trajectories that are the failures. And so we can also look at them. So here's what they look like. Wow, very nice. And you can kind of see also, you can go through them and you can kind of see how these failures come to pass. And so I don't want to spend too much more time on this, but one interesting thing here you can do is you can also kind of now investigate actually how these failures come to pass. So we can, let's see, plot the noise on the right-hand side. So this is the nominal noise distribution for the angular and the angular rate noise. Okay, and then here it looks a bit confusing, and if we zoom out a little bit, we can kind of see the noise that the optimizer has kind of found. And so we can kind of go through it and see the noise at each time step, that the optimizer shows to kind of get this guy to fall over. And of course, once we're here, let's say, there's no chance anymore. So this is I think a really powerful approach to kind of do just a basic optimization to find failures for these things. Of course, these failures are still very unlikely, and maybe you can have a better optimizer to get better results here. And so in general, this kind of very simple optimization is one approach, but in the book actually there's many different methods that are laid out to do more complicated variations on this, to do kind of failure finding, let's say through reinforcement learning methods, adaptive stress testing, so having kind of an agent that tries to falsify your system and kind of learns stuff about the state space, or multiple shooting methods, reverse shooting methods, and so on. So the book has kind of a wealth of algorithms that are all very clean, very nicely factorized, and kind of built on this basic idea here. Okay. Yes. So that already gives us kind of one of our 2 goals, right? So our goal was we are here, we're going to the regulator, we want to show them our amazing new product, and they say, okay, can you make some statement about the safety of the system? For example, what do failures look like? Can you find some failures? In this way, we have kind of shown one simple way to find failures, even in this kind of black box setting. And now the other thing we wanted to talk about is kind of failure estimation, failure probability estimation. Okay, so again, kind of the very naive way, which is quite similar to kind of naive way to find failures, is basically we're just going to do many rollouts and count, how many failures we find. Right? So mathematically, what do? We just sample trajectories from the nominal probability distribution, and then we just check every time, is the specification true or false, and then we have our super simple algorithm where we just do a rollout a bunch of times, and then this time, instead of filtering, we just compute the mean, but same, let's say. And then we get our estimate. But of course, this is exactly this issue that we discussed, that now to kind of, let's say you hypothesize that you have a failure rate, 1e minus 6 or 1e minus 9 or something like this. And of course, you don't want to roll out, many times. And especially if your experiments are maybe more expensive. So here, one rollout is quite cheap, but for example, in our lab, this has been kind of tried for work where people are drilling into the ground to find certain minerals, let's say, or have kind of other expensive, maybe medical experiments like this. And so going off of this idea that we saw that we can kind of investigate what failures look like by looking at the failures that we can find and kind of trying to characterize them somehow. what we can do is this, this really nice thing called importance sampling. So importance sampling here is, again, just kind of the first somewhat nice algorithm in this direction. And how it works here is you say, okay, instead of sampling noise from the nominal distribution, what if I have some extra idea of actually what type of noise will lead to the failures? And instead of just rolling out, regular, I'm going to roll out according to a more, designed distribution, which we denote here Q. Okay, and then maybe you can find failures with a much higher kind of rate because you know where the failures occur. But now, because we actually want to get probabilities, we need to make this kind of weight adjustment here, which kind of relates the nominal trajectory probability to this kind of proposal probability. And this is actually kind of mathematically justified. And so doing this, you can use way fewer samples if you know kind of a lot about where the failures occur, and nonetheless get this value of, let's say, 1e minus 9, but using only 1e minus 5, or let's say 10 to the 5 samples, something like this. So that can be super powerful, and again, we can have a nice, very clean implementation. We have our struct to dispatch on. We do our rollouts just like before, and now we just do this kind of weighting computation here, which just relates the probabilities of the trajectories to each other. We have again our kind of counting here, but this time with this weighting factor. It all is good. And then here's one example from one of our other works from our lab, what this can kind of look like. So here we try to estimate the probability of failure once through kind of direct estimation and once by having kind of good proposals and using importance sampling. And you can see the direct estimation has a very large amount of uncertainty, which you can kind of imagine, and only very slowly kind of goes down. And the fit proposal, the importance sampling kind of goes down very fast, and it's very stable here. And so this can be super powerful, especially when experiments are expensive or simulations are expensive and so on. And of course, one caveat here is that you actually need to have a very good idea of where you should put your proposal distributions. And so I'm not going to go into detail on that, but again, in the book, there's many different ways how you can kind of learn where good proposal distributions are and kind of propose, very, very sensible suggestions. All right. Yeah, okay, then you can also do really cool visualization. I don't know if we have time to go into it too much today. Maybe for another presentation. 10 more minutes? Okay. So actually, there's more trajectories here than I was expecting. Let's ignore for now the red trajectories. So one last thing then we can talk about is, so we have seen that we can actually find failures in our agent. Maybe it's somewhat surprising, or maybe not, I don't know. Maybe if you're in engineering for enough years, you're not surprised. And now we can try to understand kind of actually how these failures occur, right? So we were already looking at the noise trajectory, let's say, that leads to our failure, but maybe we can also try to understand actually what about the agent went wrong. And explainability, it's like a huge topic, and I can't even begin to scrape the surface on this, but the book talks about it at least to some extent. And one nice thing we can do is this thing called policy visualization. So actually the agent in the cardpole environment only has two options, go left or go right, so that's very convenient. And then we can make this kind of plot here, which is, let's say, a state space plot, which tells us, okay, we're at some certain x, so this is the location left, right, which shouldn't matter too much in the cardpole example. We're at some certain velocity, and then we have here the theta and the theta dot, the rate. And then we can see actually that this policy is quite linear, and if you think about it for a while, it makes sense. And then you can go around and it looks fine, but then if you go a little bit over here, you see that something very strange happens, which is that, sorry, maybe I wasn't clear about the colors. Yellow means, let's say, go left, and blue means go right, something like this. Okay, and we go over here, and we see that there's suddenly yellow again. So this is very strange, because you would expect that kind of, this should be pretty monotonous in one direction. And what probably happened is that during the reinforcement learning training of the agent, you only see certain parts of the domain. You probably, at some point, do a very good job at kind of staying in the center of the state space, and you're nicely balanced all the time, and maybe you haven't been, tried enough. And so essentially, there's like no data. Oops. Oh my God. essentially there's kind of no data here. And so here the agent does something, something random. And so then if we have enough noise on the model, we can see that eventually the trajectories are kind of being wiggled by the noise into this yellow territory, which is the disaster territory. And then you can see the trajectories, they go way out. Yeah, so that's just one idea, a very simple explanation. And of course, yeah, big topic, but the book also has some very nice chapters on that. All right, yeah, what else? Just really quick. So the book also has really great chapters on reachability analysis. So if you have actually a more white box model that you can query from Julia, like more in depth, you can use really great methods from the lazysets.jl package to get kind of a really beautiful, very crisp reachability analysis of your systems, let's say under some kind of bounded noise. There's a great chapter on kind of sampling failures according to their probability, right? So we can of course sample nominal trajectories, but what if we sample only failing trajectories? And there's a beautiful connection there to probabilistic programming using Turing.jl, which I can very much recommend to check out. Yeah, explainability, nice chapter, and runtime monitoring, which we didn't have time to talk about. Right, yeah, and so if I managed to pique your interest, I can recommend maybe going to YouTube, and there's actually the entire lecture series that Sydney gave at Stanford. It's all freely available on YouTube, so that's going to be Stanford AA228V, and I can highly recommend to check it out. There's also some beautiful animations that are in the lecture slides there. Wow, okay, very nice. Yes, and then finally, of course, I can recommend checking out the book itself. Yeah, that's it, thank you. So maybe as my last note, I still wanted to say, I think one thing interesting here is you can see that if a company tries to stress test their system, what they can do is they put it out in the real world, but instead of giving it only nominal, boring trajectories, they give it the most hard-hitting trajectories possible because that's how they get the info. So next time when you go to, maybe the latest self-driving car or the latest self-flying airplane, you can think about that. Okay.
Right, we have 5 more minutes before we break for lunch. So, any questions for the speaker? If not, I do have a question. So I myself work on research in the field of structural reliability. And it seems to me what you're doing is exactly reliability analysis for different dynamical systems. And I don't know if I'll trigger the right words for it because I don't work with dynamical system myself. So I work with structures. I like them not to move, basically. But what you're effectively trying to do is do first passage reliability analysis just to get the probability of time till failure starting from some initial position, right? And because your physics are complex and they involve some chaotic physics in it, you're just trying to reconstruct the response surface of your dynamical system to accelerate the process. Yeah? That's what basically you're trying to do.
Yeah, so I think that's a very good kind of model of at least some of these algorithms that you say maybe the model is black box or it's just too complicated for you to model properly. And so you basically try to build stress testing agents that maybe they manage to learn a lot about the dynamics, but sometimes what's enough is to learn kind of about the regions of catastrophe, let's say. And if you can kind of find those regions and model those regions using some algorithmic approach, then you have a kind of a very good stress testing system.
And do you find that you can do very good fit of your machine learning model on a dynamical system if it's even chaotic, even like double pendulum, say? Mm-hmm. Can you do a good fit on it to be able to do this good reliability analysis with the response surface you're reconstructing? Yeah. Or is it not a feasible thing and you need to go very deeply into like satisfying very strict tolerances in your dynamical analysis in the first place to get the data set?
Yeah, so I would say, I mean, if you have a double pendulum, I would say you don't have a chance. Because, for example, so I showed this optimization algorithm, And in the end, there's a lot of optimization-based techniques that we're using here. But of course, how optimization usually works, you try to think, okay, what little step can I make to kind of improve or decrease my optimization objective? But if you have an extremely chaotic response, the optimizer just has a really tough time. And actually already here, I found this, right? So you always roll out the kind of system and you have this card poll, and maybe previously you had a regime where you would kind of fall over to the left, but now because you've changed a little bit the noise, now already in the start, the card poll goes off to the right instead of the left, so actually everything changes. And this kind of time sequential thing has some chaotic, a glimpse of chaos, let's say, in there. Yep. And it's definitely a challenge for these type of algorithms, yeah.
Okay. Any more questions? Yeah.
Hi, great talk. Question about particularly the experiments with the agent and the reinforcement learning. One thing that I found very difficult is getting the agents to explore the state space in a productive way. Like the thing with sampling methods for like your control inputs is that you can't just have any random signal that's going to take you to some part of state space. It has to be like well designed to like get over the dynamics and take you where you are. Are there any? What's the literature nowadays when it comes to that? And is there anything in this particular package that could help in that journey?
Yeah. So first of all, I want to say I'm not an expert on reinforcement learning, but I can say maybe some things about it. Before I answer your question, I will actually say something else. So this is what we call the expert agent, and we train it in some RL setting, and then we have this interesting situation where we have this going on here. And then we trained a second agent using so-called as a student policy. So basically, you train another agent to imitate the expert, and we found that this goes away, and the student agent was much more. Mm-hmm. It's fine. I think it's not too important. So we trained a student policy, and it was much more robust, which I think is, so that's, I would say, one of the pieces of literature that I know is doing a lot of the sim to real transfer.
Behavior cloning, right? Is that what
yeah, it's very strongly related, yeah. Behavior cloning to get rid of this. Otherwise, you were asking about how to kind of efficiently explore the state space, and actually I would say that these methods we present here, you can of course also use them kind of during training. So let's say we call this here stress testing or falsification, right? So you give it like a training run, a couple of epochs, then you have an agent, then you run this kind of failure finding algorithm on it, right? You find a bunch of new interesting cases, and you put it back into the training data, and then you kind of loop this around, and now you can at least try to build a much more strong system. Well, what we're finding actually is noise at every time step that will lead you there. So we're not optimizing the state directly. We're optimizing, let's say, observation noise at every time step, such that the trajectory will go somewhere. Yeah, and then the initial condition also. But yeah, anyways.
In terms of complexity of that optimization, have you looked at like regions of initial conditions or putting distribution on the initial conditions? And maybe it doesn't matter that much for the pendulum, but in more complex systems.
Yeah. Let me give me like 10 seconds here. Okay, I think we're out. Okay, that's fine. So you were asking about kind of reasoning about the initial condition, right? And so we have a probability distribution for the noise at every time step, and also a probability distribution for the initial condition. So you can, in the nominal case, you would just sample kind of initial conditions, and then also during the optimization, it's part of your optimization variable that you try to find kind of challenging initial conditions while maximizing their likelihood under the nominal distribution.
And what impact does that have on like the convergence or complexity of the optimization?
Yeah, that's a good question. So in this particular example with the pendulum or the card pole, so obviously when you start kind of amazingly centered, it was very challenging to find failure. So one of the kind of reliable ways that I found when I made this notebook to get some nice failures is to allow kind of initial conditions that are already like the agent really has to like work already. So if you start in a very stable regime, yeah, the agent is kind of unfailable, I would say. Yeah. All right.
All right, I guess with that we thank you, Romeo, for your talk.
Thank you.